We've been talking about PageRank as a kind of score for web pages, and we had this nice notion of equilibrium values of PageRank, which regenerate themselves exactly when we apply the basic PageRank update rule. And they had this very nice property, right? So we were looking at an example, a strongly connected graph on 8 nodes, and we had these equilibrium PageRank values that seemed to intuitively correspond to the importance of pages. A is very important, C comes in second, and because C is reasonably important, G and H do a little better than E and F. Everything sort of checks out. But unfortunately, that intuition doesn't carry over on all graphs. We can define the PageRank update rule and the idea of equilibrium on all graphs, but sometimes it gives us weird answers, and we'd like to understand why that's happening. To see how these weird answers can happen, let me just change this graph ever so slightly. I'm going to replace the links that G and H have back to A, and I'm going to instead have G and H point to each other. Right? So in our notion of how the web is laid out, G and H might be like, for example, the homepage of a company linking to its mission statement. The mission statement links back to the homepage, and this is this little unit. Right? So not what you think of as the most important page on the web. And even on this 8-node graph, A still somehow looks very central, right? Stuff kind of flows back to it maybe. But in fact, once I make this change, right, this seemingly small change, something drastic happens to the PageRank values. If you work out what is the new equilibrium, there is a unique equilibrium, right? This graph is actually no longer strongly connected, but it does have a unique equilibrium. And that equilibrium, shockingly, puts half the PageRank on G, half the PageRank on H, and 0 everywhere else. Right? So as far as PageRank is concerned, under the basic rule, G and H are the only 2 pages that matters, and everything else doesn't. And in a sense, it was inevitable that was going to happen. We were sort of victims of our own intuition taken to its logical conclusion once we formalized it with the PageRank update rule. We said each node keeps pushing its PageRank on the outgoing links, and we just see how the PageRank flows and where it ends up. Well, where's it going to end up in this graph? It keeps leaking out of C into G and H. G and H reinforce each other, and all the PageRank that leaks out through C never comes back into the rest of the graph. Right? So it's like there's this drain in C, and everything swirls down the drain, and all the PageRank ends up at G and H. Right? Not what we wanted. We didn't want to say all the other pages are irrelevant, only G and H are what matters. But that is what would happen if you simply followed the results of the update rule. And the problem is, the web is not a nice little strongly connected graph like in our original example. The web globally looks much more like this thing we drew here. Right? Let's actually go back to our global map of the web. Our global map of the web had a giant strongly connected component. It had many of the pages that you want to find, and then we can position other things upstream and downstream and off to the side of this giant strongly connected component. And in particular, what we're learning here is that all of the PageRank, if we use the basic PageRank update rule, will end up downstream. It will gradually but inexorably leak out of the giant strongly connected component into these tiny strongly connected components that are downstream of it, and it has no way to get back upstream. It'll just pool there, and that will end up being what gets all the PageRank. And so if you were to look at ranking pages by this, you would say these things way out at the end of the web, these little companies where you can't get off their site or whatever, they've got all the PageRank. And it bled out of Wikipedia, and it bled out of these big news homepages and company homepages and everything. Not what we wanted. And so you step back from one of these things and you say, either this is like a completely fatal problem or something where one more idea is going to fix it. And what's nice here is that actually one more idea is going to fix this. There's one small thing we can do. We can preserve almost everything we had already and get a measure that actually corresponds to intuition and still has these nice mathematical properties. And to motivate this new measure, let's continue the fluid analogy one more step. And let's ask about fluid, say, on the surface of the Earth, right? There's a water cycle where water kind of runs all around the Earth and ends up in certain low points like lakes and oceans. And we could ask, why is it that all the water on Earth doesn't just pool in the lowest points on Earth, leaving everything else completely dry? All right, okay, maybe this is carrying this analogy a little too far, but if we think about it, it's because there's something else going on in the water cycle, which is stuff evaporates, right? Water evaporates out of the lowest points, ends up in the clouds, and rains back down uniformly over the land, so it ends up back in these high mountain streams, which become rivers, and they continue flowing. So there really is a cycle, right? The water actually ends up both at the low points and at the high points. And that's what we need here. We've created a system where everything just pools at the low points, but it has no way to get back out. So let's finish defining the full water cycle that we'd like to happen for PageRank on the web, we need a way for PageRank to evaporate back up and be rained back down over the whole network. That's not hard to do. So we're going to take the basic PageRank update rule. Each node divides its current PageRank into equal shares, passing it across outbound links, and we're going to modify it just ever so slightly. We're going to modify it by adding a scaling factor, this number that we'll call S, a number less than 1. And this effectively is going to be some kind of evaporation parameter, some kind of constant controlling evaporation. And here's how it's going to work. We're going to have a new update rule, which says first, apply the basic PageRank update rule, like you did before. Now we're going to evaporate off some PageRank. So we're going to scale all the PageRank values down by a factor of S. Right? S is less than 1. In practice, it's something maybe around 0.8 or 0.9, somewhere in between there. Okay, that gives us a supply of excess PageRank, right? 1 minus S leftover units of PageRank that have evaporated off the network. We're going to distribute this completely evenly across all nodes. Okay, so it's going to rain back down over the whole graph, 1 minus S units divided evenly over all n nodes of the entire graph. That means if stuff has been flowing out of, say, the giant strongly connected component, it can get brought back in by evaporation and then by this raining over everything. Okay, that is the scaled PageRank update rule, those parts. Apply the basic update rule, scale everything down by S, take the 1 minus S leftover units, divide it up evenly over everything. Right, that's one update. And now we have a new fact, right? So as promised, most of the mathematical machinery from the PageRank update rule has been preserved here. We have a new update rule. It looks sort of like the old one, but extends it. And the new fact is that repeatedly applying the scaled PageRank update rule in any network converges to a unique equilibrium set of PageRank values for all networks. So in particular, the equilibrium is unique, and it is something you can reach by just repeatedly applying the rule. This is now the endpoint of this process because these values, these scaled PageRank values, actually make intuitive sense in basically all networks. And so when, for example, we have this giant strongly connected component, it manages to hold most of the PageRank inside it because it's just so massive that it receives most of the excess PageRank that evaporates and rains back down on the network. And these things hanging off of the giant strongly connected component only get a small amount. So this, in the end, is what we think of as the definition of PageRank, and it reflects a lot of the intuition that we've built up. This idea that experts endorse other experts, or that we can find good pages circularly by knowing where other good pages are. And that if we use this principle of repeated improvement, we can keep refining our estimates, ultimately arriving at an estimate of high-quality pages that we can use for ranking search results.